All right, we are back. Um, and we are going to pick up where we left off yesterday and utilize some work that the FabWorks team did over the day, which was to make the design better by moving the flexures inboard, which is really cool. You can see it in the video here. So we're going to incorporate that change and we're going to do some calculations. But first I'm going to share, and then we do that. First, we're going to do some calculations. So we're going to figure out what the new allowable stress is based on this new loading condition, if this is willing to share, which doesn't seem to be. There we go. Okay. Okay. So a couple things changed. I don't have the CAD for this, so we're going to have to draw from scratch. But let's take a look at where we left off yesterday, and we'll incorporate some of these changes once we draw it. And we'll make it parametric too. That'll make it more fun. Actually, we'll have to make it parametric. So yeah, the tabs are on the inside now, which is great. And we'll actually pause this when we get to the point where we can actually look at the detail. There we go. That's the detail. So we're gonna draw that, and it's kind of cool. Actually, we'll draw on top of it. So can I make this bigger? No. So the idea is this was our original L, our length. They went ahead and doubled it by having it pull back on itself, which is cool. There's only two of these locking tabs, which I guess is really all you need. But you double the effective length of the cantilever. So this is, I think this is clever. Now there's some downside to this, and the downside is you induce some torsion, which actually does matter in terms of stress. And I will explain why. First, let's explain why we're in torsion now. So originally, we were just a cantilever beam from here to here. And so when this was one, let's just call this one, we'll just draw the section here. It was just this. And actually, we should draw this in isometric so you can see exactly what's going on here. So this was our beam, and this was fixed. We had our load here. And this L went from here to here. Easy peasy. But now, what we have is this. Calling it a snake. So this is fixed, and we apply our load here and draw it this way. Now why is this different? So this one was on axis right at the center. So there was no torsion. You had shear, but shear doesn't matter in this case, and I'll explain in a second why. Here, we have both bending moment, so this is effectively the same as having this springboard be all the way over here in terms of bending moment. Um, I think that's true. We'll evaluate that, but I think that's pretty much true. But the difference now is we've induced torsion, and torsion is just an eccentric load, which is off axis from the centroid of the second moment, or the off axis from the centroid of the fixed condition. So right here in the middle of this, that's the centroid. And now that distance from here to here, we'll call E for eccentricity, that's now inducing torsion. So now we have two stresses going on, and it's happening right here. The first one is bending stress, which we've already talked about yesterday. MC over I. But now we have this new one. And it is torsion, which is equal to TR over J. And this R, I have to rethink about for a closed section that's not round. It's a closed section, but it's rectangular, so I have to think about that. That's essentially our C, I think, in bending. Now, the eagle eye viewer would go, well, hey, actually, torsion is just shear stress. And you had shear stress here. What's the deal? Well, the deal is, when you look at this section here, let's draw a section that looks like, let's do a section view, actually right here, AA. When you look at section AA, actually I have to scroll down for this. When you have a section AA like this, essentially we are, let's see if I can get this view. Okay. We have this beam, right? That's looking at section AA. And if we rotate that third angle projection, it looks something like this. So we're looking at that right there. Now, the reason why the shear stress didn't matter yesterday was because it was pure shear or transverse shear. What does that mean? So when you actually put an element into bending, you develop transverse shear and you develop shear. Transverse shear is shear. They're the same thing. They just act in opposite directions. But the reason why this matters is because when you look at this section here, and there might be a better way to draw this to make this simpler to understand. No, I think we're going to have to do this. So here's the hatch section there. And when you rotate it 90, you get this. And remember, this is fixed. And actually simplify this by just drawing this out. Okay. Just assume that this length is correct. So when you apply a load P, you get bending stress. And that bending stress looks something like, if we were to actually draw it out, we'll call bending stress B. It's not uniformly distributed. I think it is, remember, it's MC over I. So bending stress is highest at the outermost fiber. So if it's 0 here, right, that's the center, it's highest here. And so what that looks like, I think, is like this. And so that is the distribution of our bending stress, and I think it's linearly related. Now, when you look at shear stress, we'll draw shear in green. That actually looks like this. So let's call this a 0. I believe it's parabolic, and it looks like this. And what this means is it's 0 at the outermost fiber. So right here is 0, and right here is Vmax. Right here is 0, and right here is moment max. Let's call it M sub n. Now you see what happens. You have the most shear in the center of the beam, right here. And you have the most bending stress up here. So you can kind of ignore it when you're just purely in shear. That's why whenever we do bending stress calcs, we don't really look at um, shear stress. And to double check myself, I'm going to double check this. Yeah, okay, it's parabolic, and I'm not an idiot, so that feels good. This is what it looks like. It's maybe hard to see that, but um, so that's a long-winded way of saying we don't care about shear stress generated by that load. Now, now we're talking about something different. We're talking about this. The shear stress is now torsional. Now, why does that matter? It matters because if this section, so going back to the example we had before, we have a fixed condition and a beam, and you apply the load, but it's off center slightly, like this, right? This eccentricity creates torque. Now that torque gets applied differently. It doesn't look like, we'll use orange for this. The shear stress isn't distributed um, towards the center. Remember, the equation is TR over J. It looks a lot more like a moment. And so if this, for a rectangular section, I'm going to rotate this 90 degrees here. For a rectangular section, that means here's our centroid, and that means the highest torsional stress is actually going to be the distance here, which is R, which means we actually have the highest torsional stress at the outermost fibers here. And so that actually looks like, and what I'll do is I'll draw, let's imagine that for a second this is actually a circular section. What this means is you actually have the worst case torsional stress, the same place you have the worst case bending stress. So you now do have to account for it. And so that stress actually looks, this is not big enough, so I'm going to use it. I'm going to actually just go look at an image of this, because they will have a nicer sort of image for us to look at. Yeah, this is what it looks like. So you can see what's happening. The highest torsional stress is actually at the outermost fiber. And so now we have to do a combined loading thing, which is more complicated. It isn't too crazy because this is a simple shear and normal loading case where you can actually just take the square root of the squared values. And we'll double check that too. But I think you just take the square root. That's what we've done in the past. All this to say, we're going to be able to find an answer here. Shear stress. This is for a pressure cylinder. Here we go. This is actually Now, this is not combined, this is additive. That's simple. Let's look for a combined loading case. Bending, axial, nope. Whenever you have axial and bending, that's easy because you just add them together. The problem is we're actually acting at a 90-degree difference between the two. And so you have to get more complicated with how you actually get the right theoretical maximum stress. Let's see if we can find a good example of this. I'm speed running, making the most boring mechanical engineering stream, and I think I'm going to set a world record here. But bear with me, we're going to get to CAD here in a second. So yeah, this is it. So a couple things. For you have to know what kind of material you're analyzing. So we're analyzing aluminum, and I know that aluminum is ductile. Ductile materials are checked against shear stress. And you check it by combining it like this. And so f sub y goes to 0, I believe. And then this simplifies to the square root of the normal over the shear. If we can find a good rundown of that somewhere. Conversely, for brittle materials, say like a hardened steel, you actually, I mean, you do care about shear, but you actually check maximum principal stresses for failure too. But for ductile materials, we use the, I believe it's called the von Mises yield criterion, which is built around energy, but for first order stuff, you can just look at shear. Okay. Oh, I think I should have said torsional. And that will probably spit out what we're looking for. Let's do this guy's great, by the way.
Oh, it's
Oh, it's not the one I was thinking, but either way, he's gonna spit it out here. Yeah, you get the equivalent here. And he really went after it on that. I'm not gonna do all that. All right, you're gonna have to trust me on this. I'll double check this later, but essentially, when you combine these two, you get your new theoretical shear stress. Actually, let me look at the Wikipedia. I think that actually says this. I remember that. Let's see. Hmm. I want to pull out my book, but I don't want to get taken down for it. Okay, here are the equations. So we're looking for, which one is it? I believe it's this one. All right, I'm not gonna burn time on this. Let's just get back to work, and I'll double check this later. So essentially, our maximum shear is tau max, which is equal to the square root of the bending stress max plus bending stress squared plus tau squared, or the maximum shear stress. And so that is our new value. And so you'll notice that this double back feature actually is going to reduce some of the capacity we initially had, because this value is not zero. Now you can imagine if you move e to 0 and you put this back in line, this term goes away, and this becomes the square root of the stress squared, which is just the bending stress. So interestingly, you can actually see it cancel out. So this is the equation we're driven by right now. And I will, like I said, come back and check this later. So let's actually do let's write some stuff down that we're going to do today. I believe we did this. So we're going to do and then I actually want to create a plot. The length, how do I nest this? So we're going to chart X and Y, and actually we'll figure out what we're going to show exactly. But it's going to include this. It's going to include load. It's going to include length. It's going to include, what else would be interesting to see? Young's modulus. We don't really care about that. Length, thickness, or gauge. These are the initial things I want to show, but I want to show what happens as you change these values over a plot. I think that'd be useful. Hello, hello. So that's our new to-do for today. But first, let's draw this. Make sure they haven't set the CAD, because if they already have the CAD, then it's going to make this simpler. No CAD. That's fine. We'll draw it. So let's draw this first. And first things first, let's delete all this. Let's delete all this. We'll erase history, and then what I want to do is I just want to pull this, essentially this section and this tab detail here, because I think we're going to salvage this. Yeah, because we want to keep this tube size. So I'll do that now. Let's get some dimensions real quick. So what was the thickness they were using? It was, the thickness of the cut is, looks like, sorry, delta Z, 0.86. So we'll create some variables here. And it's rounded up to 0.87. What else did they do? Thickness of the material. It's probably good to know. 1651. Okay. And then the overall size, I think, was 50.8. Yeah. so we'll want those variables for later. And we'll cut this. Then we will move this to the center of our entire CAD model, because that is going to help us simplify things. It's my coordinate system. There it is. Is that on center? Yep. Okay. And I think that's fine. What's our distance here? Almost 15. Okay. Okay. So here's our tube. Now we're going to cut out the shape that they had up here, which is that sort of Z looking thing. So we're gonna have to make this up as we go. I already cut, paste that earlier. Just use that here. Real quick though, I do want to clean this up first. Okay, let's go back to that screenshot. This is what we're going to draw. What was the thickness? What was the clearance they gave themselves? I bet it was a thou or two or something like that. So that would be this 1.905. So 65 minus 0.19, 1.9. So 25. They gave themselves 25. They gave themselves 250 microns. So I'll actually add that as a variable here. Try and make this all parametric to make the nerds happy. Okay. So let's get to drawing. So the orientation is going to be, actually let's get this sort of oriented as though it's representing the cutout I have over here. And actually, the easier way to model this is going to be doing a negative modeling, I think. Like you model what you want to cut out. Yeah, we're going to model what we want to cut out, and then we'll just boolean that from the tube. So we'll actually do that on the tube though. So let's do that. Just going to draw the, yeah. Okay. Get this constrained properly. Okay. So let's pick up a hard distance from the edge here. I think we said yesterday that was going to be 50 or something like that. It's really just a minimum edge rule. I guess we can get away with like 30. No, we'll wait till engineering results come back and tell us that we actually need more clearance. Um, okay, and so then what I'll do is I will get to the center of our rectangle, and this is going to be the tube size one, and then I'm going to set this equal to that. Okay, and so now we can modulate the position of this based on what edge distance we want from here. And so we said we wanted this to be 25. We're actually going to delete that. Actually, no, what we can do is just set a coincident constraint. And then why isn't this done yet? Okay, then we'll make that perpendicular to the coordinate system of the entire part. Okay, so this is our work area now. This is the outline of a tube. Now, it looks like they've got maybe 3/8 of an inch from wall to feature, but we're going to kind of make that up. So we'll just do some minimum distance here of what's 3/8 in freedom units to metric. Roughly 9.5, so we'll just call it 10 millimeters. Looks a little too much. And then this is going to be that. So now we have our true work area in here, I think. Looks like they really cut it close. We might be able to get away with that. Okay, so let's look for some symmetry. Can we actually mirror this? It looks like it's mirrored twice. One about an axis here and another about an axis here. Oh, actually, first we have to draw these tabs. That's going to define the rest of our geometry. And as a matter of fact, I should undo what I just did there because that is going to be the driver for our geometry, is where those tabs land. And when I say those tabs, I mean these tabs right here. They're determined by the wall thickness and the actual tube. So we'll draw that now. And I'm going to make this a construction geometry. So we'll have our tabs, and actually I'm going to find my symmetry here. So I only have to draw this once in the mirror. So what are these tab dimensions? Looks like, oh, they added a little chamfer. That's clever. So it looks like you need this cutout size, which is 8. That's right. Yep. These are 8. So this is going to be 8. And then interestingly, it's going to be 8 plus 2 times the clearance. Weaning that clearance. And then the thickness is going to be the material thickness plus 2 times the clearance again. And then position we have to measure, and the center is going to be, draw a sketch here to really figure this out. So the distance to the center was 13,335. And let's see if that's true. Wait, why am I off center here? Did I goof this? No, they goofed it. Right? It doesn't look like it's centered on the world coordinate system. It is. It's just the delta here isn't. So that's maybe some modeling error or something. Actually, it might be because of the draft angle on these tabs. So I won't put too much effort into that, and I'll just assume that this is going to be symmetric. So what's actually the distance to the centroid? 12065. You know what? I like edge distance more. Let's do 13335. And I'm going to turn off animations because it's driving me nuts. Okay. So we said 13335. So now we'll draw that in here. And we are done with that. Okay, so now we should be able to mirror this geometry. Sorry for the dog. Okay, so we have our tabs. We need more space though, because that's where they sit, but we also need clearance for the insert. And it looks like they get the clearance. So we're actually looking at it, yeah, this way. How do I rotate? It's not letting me rotate. Weird. Oh, there we go. So we actually want to do like that. So okay, so we want these tabs to come down, and I'm guessing it's just essentially we're doubling the thickness there. So we're going to come down, I guess this, actually, let's look at the geometry here. I bet it's just this distance. So they use 8 1/4-ish. Yeah, 8 1/4-ish. Okay, so we're gonna clear, I think we just double this distance up. Mirrored about that. I think that's right. For some reason, this looks like it's about to interfere with the edge. Yeah, so they must have moved this. This 1335 turned into something else. Um, so let's go to 10, see what that does. It doesn't work. So that moves us closer. It looks like an offset. Let's do, how did they, it looks like it's just a move. So I can't do the mirror thing. Um, I don't think I can do the mirror thing. So that's kind of a bummer. but we will manually model this. So this turns into, this is equal to this, and then this is equal to this, and then now we control this placement, and that is going to be, so we said this is 1335. Maybe we just see what this gets us. 1335. I think that's right. And then we presumably can now mirror this geometry. And I think we do, no, that doesn't look right. All right. You know what? It's a case of let's get it to work outside of the tube and then we'll offset it. I think that's what they did. They just figured out this geometry and then figured out where to center it on the tube later. So we'll do the same. I think we're getting too far into the details of making it work within the sketch, but we don't really care about that. So let's just get it to work first. Okay. To reiterate that point, I'm actually going to turn off the 3D. Okay. Now, actually thinking out loud, do we actually need to double the distance? You really just need this distance from here to here, which is double the distance anyways. So yes, we do need that. Okay. So this goes to 16. It's more palatable. And it looks like this falls right on the center. So that's good. And so we'll model this first tab. Yeah, we'll model this first tab. And I think we might be able to just do some symmetry and mirror it over. Actually, let's do separate sketches for this. I have a feeling that's going to make this easier. Like I said, I'm going to turn off the 3D and just model these extrusions out. Turn off the sketch. We'll do some sketch linking here to make this work. Actually, let me pick up the plane here, because I want to sketch on that. Okay. I'm going to project this. I think we're going to work on this side only, right? Yeah, I think we work on this side only. Okay. Let's get to sketching. So, I'm going to pull a center here. And we're going to have a tab. I don't know what that distance is going to be. Looks like twice this thickness. Guess we can eyeball it. Is it also going to be 8? I think 8 looks right there. Yeah, they probably used 8. All right, so now we're going to draw this, and I think this comes coincident with the bottom of the slot here. And then what was the, actually, I think we had this from the calcs yesterday. The width of that tab was 6.4, let's call it 6.5 for now. So this width is going to be 6.5. Actually, let's parameterize that. We'll actually call it what it is in our calcs. So I can call this B. And obviously something's going on here because we picked up the center, and I don't know that the center is going to work. What do we do wrong here? No, it's right. I think their B is just smaller though. So let's bring B down to 5. Nope, 4. Yeah, it looks like 4. Okay. And then we give ourselves some distance to this edge. So let's actually just draw the snake out, and then we'll start dimensioning it. And we will, this is going to keep wonking around, so let's just start piecemealing this. That looks like 4. They love multiples of 4, don't they? Well, this didn't do anything. This did not behave at all like I wanted it to. That's fine. Okay, so I think this was, there we go. So this distance is going to be B. We're maintaining the same width. And then this is also going to be B. And this distance is the slot cut width. And that is going to be cut thick 1. And then this ends up being flush with this roughly. But I'm curious how to think about this. Okay, so actually this is wrong. We want to do, skip this back. Okay, now we're looking real. So now this distance is going to be, again, B. And this distance becomes B. Now, we are almost done. B. Now we pick this length. Actually, how's this length getting decided? There we go. It looks like we are the cut thickness away from that. Okay. And I think we're right. Yeah, I think we're good here. I think this is right. Okay. And so now I'm going to work from solids to Boolean on this. I think it's going to be simpler than trying to think through this in terms of sketches. So these are the cutouts. This is the tab we're going to have. And while we're at it, we're going to, oh yeah, we're actually going to have to cut the cut thickness away from that. So do that. It's going to make sense here in a second. So this turns into Yeah, I think we have to close up our sections here to actually make this do what we want logically. Okay. Okay. So now we have what we're going to cut out of the tube, which is this. Oh, I haven't cut out the full. I have to cut out the what we're going to cut out as well, not just the tab. Um, so this is going to get just bear with me. Essentially, I just have to actually draw what we're going to cut out here. Right now, I've just got the tab modeled, and I don't have the actual boolean that we're going to use for the cutout. So let's just look at that. It'll be relatively easy to model, I think. So this goes cut thickness away. Essentially, I'm just using cut thickness everywhere. Why are you not working? There we go. We need, yes, we do need to cut out here as well. So here's our tab. Okay. Now we can create a subtraction boolean. Right? Right? We'll see. Okay, let's turn off the sketch and see if we can start making sense of this. Bring our tube back. Okay, let's test this out. So from the tube, we're going to subtract this to get our tab, and then we're going to subtract the... Ooh, that got complicated. Why did that get complicated? Okay, it's because this boolean needs to change. And I'm going to brute force that, and I'm sorry that I'm brute forcing it, but, you know, I'm here to get things working, not do it perfectly. Okay, so now this looks real. This looks like this, roughly speaking, depending on who you ask. So let's add some radii, clean this up. And actually, before we do the radii and clean up, let's see how we get this pattern mirrored over correctly. So, I'm going to do that by keeping my tool body. And let's think through how this actually mirrors over. So this is centered. Yep. So we should be able to mirror this over using the world coordinate system. And then I think we need a centroid, we need a center plane to do the final mirror. So I'll pick that up from these tabs. So again, we're going to mirror this over. We're not going to keep the original using the world coordinate system plane. And then we're going to do that again about our new center plane. We're not going to keep the original. And that should go into the right place. And by golly, it's almost like I know what I'm doing. Look at that. Watch it not work. I don't have to eat those words. All right. Is that correct? Almost. Almost. I have to eat my words. That goofed. Why did that goof? Because I didn't fix this one. I'll fix that one real quick. Again, not the prettiest way to do this, but it is an effective way to do it. Okay. I can not eat my words anymore. Okay. So that is what they have modeled there. I think that's going to work. Let's test it out. How about that? How about we test it out? So you rotate 90, then you rotate 90 again. Yep. Now let's put it into place. So we pick up our tubes, we walk it over, get it roughly lined up. Have hidden lines turned on so I can try and find that. It's actually that slot right there. So we're going to go right there. Almost. Bring that back just a hair. And so now you... Oh, we rotate this 180 actually, because we have it oriented incorrectly. Okay. So you push it in, bend those tabs down, like so, and then I'm going to make the sound effect, click it into place, and then it should work. Looks like we have a little interference here, so that's kind of expected. This wasn't perfect. So these tabs have to get modified slightly. It looks like we're going to move them half the thickness. And that's fine. Which way though? Towards the hook. Oh, I forgot to add that radius back. So these move half the thickness. I think it was 4. Why didn't that work? Is it more than 4? What's going on? Am I hallucinating? Oh, I think do we have to recenter them? Oh, I did it too late. I have to go back in history and fix that. All right. It's hard being a proponent for direct modeling when I do it incorrectly. Both need to be in the same direction. That looks like it works to me. Is this gap too much? Did I overdo the gap? What am I... Do I just need to... What am I doing wrong here? All right. I'll figure that geometry out later. What I'm more interested in is doing the calcs on this. Um, no, I should actually figure this out before we get back to calcs. Why is that not working? Did I move it the wrong way? So that's in the right position there. Made these hooks smaller. I think that has something to do with it. Is this? I think it's off center. I think that's why mine isn't off center. So go back to the original hook size. Then when you move it over, oh yeah, that's kind of it. We need to just move. We need to do some offset, non-symmetrical offset, which is actually bad because that means that the system isn't. Yeah, that's actually a bad thing because it means orientation matters, which means this isn't. Yeah, that's not good. So that's a flaw. We'll get to that in a second. Let's just bring this back to correct, and then we'll do our offset. So I think we have to offset this one some distance. I think it's 4. We're getting awfully close there. I don't know what's going on, but yeah, orientation will matter, I guess. I don't love that though. So let's see. So this works. When you slide it in, click, and you're in. So this works. The problem is we're getting awfully close to minimum edge distance here, and it looks like they got around it somehow here. And I don't know how they got around it. Like this distance is bigger than this distance, and I don't know why. I mean, it might just be that's the edge distance. No, I think yours are mirrored too. Like if you rotate this 180, it actually doesn't look like this. I think yours are mirrored too. Okay, this edge distance isn't the other end of the world. It's 3.63. I mean, where's our load actually going? Um, I guess it follows the entire perimeter. No, it actually, we do want this edge distance to be a little bit better, but well, I think it's because of these tabs have changed size, but it doesn't matter. Well, I'll wait to get the cat from them before I start making too many assumptions. In the meantime, Let me get this oriented exactly correct, now that we know that it works exactly correctly. And how are we going to do that? I think I can brute force it. Brute force it by using the cut thickness, or actually the offset distance. So that's actually going to sit on this edge. And then this should be half of the, no, it's one offset distance, I think. Or clearance, I mean. And we'll draw a section to prove it. Yep, that looks right. And I guess it doesn't matter too much, but yeah, I guess we'll get it right. And this one's minus that offset too. All right, so that is a joint. Um, the way you have it drawn, the latch will not snap into place. Oh yeah, you're right. You hate to see it. Well, did you make those smaller? It's hard to see from this video. Did the tabs get smaller? It's hard to see. Yeah, those tabs must have gotten smaller then. Well, I guess the tab size is kind of given to me here. So the answer is yes, they did get smaller. Oh, it's the distance between the tabs that changed too. I see. So it's this distance I need to be thinking about, which is roughly going to be 4 millimeters, I think. Yeah, 4.3. But this is solvable. So the back one goes up 4.3. That moves 4.3 in. Yeah, this is a giant pain. Next time I'm going to wait for the CAD. Yeah, that's enough to get that one on the left in. Okay, I see what's going on now. So I have to move these 4. This one moves in 4. All right, send me DM, but I think I might have figured this out. If this doesn't work, then I will eat crow and start making some changes. That's starting to look more like... Is it though? All right, I have to look at your DM. So I have no idea. All slots are offset in the same direction and mine are mirrored in. Okay. But if I move these 4, then it interferes with this. Let's see. Jonathan, did you change the um, prongs? Did you change the prongs at all, or are the prongs the same? These guys. Relative to yesterday, I mean. I think that might be the problem. All the arrows like in my DM in your design. Draw the arrows. What arrows? Hmm. All right. This is fine. I'll figure this out later. For now, though, this is close enough that we can do some of the analysis. Um, so we're going to check for combined loading here. Um, and we're going to ask ChatGPT about that. See if it actually gives us an answer. I got agent going. I haven't actually used agent before. All right, let's try without agent. Actually, we'll let that cook while I keep going here. Okay. So and what is the polar? So J in this equation, by the way, this is a polar moment of second polar moment of area. You can think of it as second moment of area, but for rotation. Let's go find these values. Actually, I think you just take the z value for this. Let's see if they have it. They do not. So it's really I sub z. So j is equal to I sub c, right? What is it for a rectangular section? Polar moment of, oh man, that's gnarly. Rectangular. What's the difference between j, polar area moment of inertia, z sub p? This thing is still going. Um, yeah, what is our j here? Let's see. It is going to be rectangular, so. What's this? To log in? I've never used ChatGPT's agent thing, so I have no idea what it's doing. Um, what? Oh, we have to log in for this. I'm not doing that. Second polar moment of area. Incorrectly, polar moment of inertia. Yeah, see, you have to be careful with inertia because I think it implies some pi to mass, and we're just looking at a section here. What was the value they were giving us? Homeland area can be insufficient to analyze beams and shafts with non-circular cross-sections due to their tendency to warp when twisted, causing out-of-plane deformations. In such cases, a torsion constant, yep, that makes sense, should be substituted, where an appropriate deformation constant is included to compensate for the warping effect. Right. Yeah, that all tracks. I forgot about this constant you have to apply because it's non-circular. This is way more straightforward for a round shaft. Essentially, this is because it's non-uniform at the radius. You get this need for the torsional constant. So you get the polar. Yeah. Here's our torsional stress. So now we need to make this even more complicated. Sorry. Torsional stiffness, blah, blah, blah. Ellipse, square, rectangle. J is beta AB cubed. Oh, this is easy. This is nice. A over B. Okay, so we're getting there. Um, hey Bryce, thanks for jumping in. Could you just email me that geometry and I'll just copy it in? Um, that's probably the easiest way to do it. Um, I'm looking at your messages on X, by the way. Sorry, there's like 5 ways to get in touch through through these platforms. It's actually the first time I've had to do this for a rectangular section in a while. So, yeah. So what's our J here? So we're gonna have to calculate J. Ooh, actually, I bet you we can pop this into ChatGPT. and get a good way to approximate the value here. What was it called? Beta. Call this W. So this is the greatest use for AI for me right now. It's like little tasks like this. This would have taken me 30 minutes to write, but it just spits it out. It's phenomenal. Okay. How do you do this inline? There we go. So we'll paste our ChatGPT code. W values, blah, blah, blah. Get beta. Great. Okay. So our A and B here are actually B and H. Let's look in this chart and see what it is. A is the minor radius. Long. Okay, so A is long. B is short. A is long. Need to write a little for loop. Is that right? Um, I forgot how to write Python. There we go. Okay, so then we get, what was it? Uh, let's get ChatGPT cranking on this first. Okay, so what do we have? Is it second polar moment of area? Hey, look at this. We'll get back to this in a second. This is cool that took 4 minutes to do, but it did it. Um, so for a rectangle, it's this. Okay. A is the long side. And I wanted to, oh yeah, that's right. Is it second moment of area? Or is it first moment of area? I know it's second moment of area. Yeah, second polar moment of area. Make it a new line in Markdown. Clean this up later. Okay. So we're going for J. Here's the example. I'll leave this for now. So you might want that later. We don't need a call function for this. I don't know why I did that. Well, in that Python code over here. Wait, what is this? J is equal to, I think I got this backwards. All right, thanks, Bryce. I'll take a look at that in a second. Yeah, this is backwards. Uh, A is B, and then I've totally complicated this. All right, so we have to have, no, that's wrong. Problem is I had B and H declared before, so now I've got these A's and B's all over the place. So this will be A. So what I'm going to do is I'm just going to add a suffix to delineate that we're talking about second moment, polar second moment of area calculations here. And then B is equal to A. This is ridiculous. Are you confused yet? Because I am. So originally it was B and H up here. B and H. Well, actually, we know that B is always going to be bigger than H. So we don't need the loop. We'll just simplify this. We're just going to simplify this. Because we know that it's never, the thickness is always going to be the smallest. And we said A is the length of the long side. So A is long, which is B. And then B for this equation is equal to H. That's the short side. Okay. Okay. This is terribly confusing. I'm sorry. Don't blame me. Blame mechanical engineering software being terrible. Looking at you, MATLAB. Okay, torsional constant, which is our beta. So beta is equal to, and I think we have that written out here somewhere. I think we get beta. That's right. We look it up. So we use a bunch of float interpretations here, which I don't hate. Float MP, blah, 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 blah. Let's just print this out real quick to see if it worked. W, that's right. W doesn't actually exist yet. So W is equal to is A over B, right? Yeah, A over B. Great. And I don't know why this is spitting out the comments. So we're just going to delete that. All right. So what is our A and B? Let's actually go look this up manually and double check that it works. 3.88, 3.88. It's in between 2.63 and 2.81. And 2.7 is that. So we are cooking. Okay, so now we can spit out the actual second polar moment of area, finally. J. Actually, J's not going to really mean anything to us. But I do want to see units. Millimeter to the fourth, that is right. Second moment of area is always in meters to the fourth, in case you're ever curious. Okay, we're getting there. We almost got our torsional stress here. And then finally, torsional stress is, mute this. Torsional stress is TR over J. So tau, well, tau max is equal to T R over J. We have our J, we don't have our R yet. So we have to calculate first T. Torsion is going to be, remember from this diagram, torsion is actually, I'm sorry, torque is equal to E times P. In other words, the load times the eccentricity. So let's figure out, let's figure that out. So E is going to be, E is essentially the distance from this centroid to this centroid. How can we do that? Just sketch it out real quick. So yeah, it's going to be the center point here to this distance here. This will be our E. That's 5. And then we want P. And remember, this bit us yesterday, our load was always off by a factor of 4. So we're going to fix that before we get confused again. So P was, yeah, 31 divided by 4.4. Yeah, that was the total load. So we're going to normalize that. We'll call it P per tab, or P sub, we'll just call it P sub underscore. And that already has units, so that maintains its units. Okay, and so now we can get T. So T here is equal to P sub times E. And then we get R, which we actually have to calculate. This is actually going to be a trigonometry problem, I think, right? So you have a center here, and R is essentially this distance here. How do you calculate that? Yeah, how do you calculate that? Is it 0.707 because it's 45 degrees? Oh no, it might not be 45 degrees. Damn. We have to do we have to do some trig real quick. So we have our center here. This is H. This is B. This is our triangle. SOHCAHTOA. Which one do we want? So we know A. We want H. So we know A. We want H. So we don't know this angle though. Darn, how do you do that? Oh no, but we do know H as well. So we know this, and we know this, and we want this. So it's, what is it? Opposite over adjacent, I think. So we know these. We don't know this one though. There's always been a simpler way to do this, but I always I always do this the long way, which is embarrassing. But um, wait, we want hypotenuse. Chase opposite over hypotenuse. We can do one of these, but we need another angle. Oh wait, isn't it? I used to do this in statics all the time. I forgot how to do this though. think it's just a ratio. I think it was a ratio of squares. I can't remember. It's going to be so embarrassingly simple once I see this. Yeah, c is a squared plus whatever. That's embarrassing. Like I said, I always don't do this because I always trust solving for angles and stuff, which is probably the wrong way to do this. So I'm learning how to do it the right way now. Anyways, all that to say, um, this is b over 2. This is h over 2. This is going to be my e value that we're looking for. And so e is equal to the square root of b over 4 squared plus h over 4 squared. All right, we're getting there. So what's our e? This, how did I get this e? That was stupid. Forgot how I got this e. It's wrong. I also don't know how to spell hypotenuse. How embarrassing is that? It gets worse and worse. Hypotenuse. Hypotenuse. Okay, so now we have e. We have p. Oh, we were calculating r, not e. What was I thinking? E was 5. Really embarrassing day for me here. I did wake up at 4 in the morning though, so let's be patient with me. I've been up for a while. All right, so we have our E, R, all that fun stuff. Um, so this, just to put a bow on this so everyone knows what I'm doing, this was R. R. What's that? Okay, I think we're getting there. I think this is going to be, I think we have the answer now. So we're going to find out our max stress here. I'm going to delete printing the polar moment of area, second polar moment of area. And of course we get some issues here with units. So what do we got? Why is this breaking? You can't divide? Oh, I keep forgetting. In Python, it doesn't know what a hat is. You have to double multiply. All right, so what is this in KSI? Nothing. It's essentially nothing KSI, which, um, thanks, Sahib. Thanks for the kind words. Um, okay, so that's very little. So really, this is not going to matter. But it's good to do because we want to be sure. I mean, this is less than 5% of a kip. So 50 psi. Yeah, 40 psi. It's nothing. Okay, so now we'll combine it. And let's go look at what ChatGPT spat out earlier. Took it 4 minutes. So combination of normal stresses and shear stresses depends on what you need to compute. By the way, I would normally just walk over to which of my books has this. I use Shigley's. I like Shigley's these days. I used to be a Norton fan. Robert L. Norton's machine design fan, but now I'm on Shigley's because they include a bunch of stuff on weldments, which is really nice. But I don't have it in front of me. And like I said, I don't want to get taken down for showing you pages of a book. So we're going to trust ChatGPT. And actually, I know that this is right because I remember looking at this recently. So normal stress gets divided by 2. Plane stress, blah, 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 blah. Maximum principal stresses are this. Really, you should be checking more than we're going to do. But this will be fine. So for the rotated planes, by the way, these are at 45 degrees. Yeah, these are at 45 degrees. We're not looking for max and min. We want to look for the equivalent stress, which is this one. So theta x is 0. We only have one of these. So this normalizes to, yeah, this is it. Yep, this is the equation. ChatGPT did it. Love to see it. It even gives you the source. That's fantastic. I think I'm starting to like AI a lot. What did it say when it cited this? Only one. Theta sigma v. Let's find sigma v. I think it made this citation up. I don't think it's actually cited in here. Three over two. Yeah, here it is. So 2D. We are in a 2D application. So these go to 0. One of these goes to 0. This one goes to 0 because it's multiplied by 0. So you get normal stress squared times 3 times the shear stress squared. Yeah. All right, so we verified that this is indeed what we want. Can I copy and paste LaTeX? See if it lets me. Nope, no LaTeX. So sigma bending squared plus 3 times tau max squared, and the square root of that. So our equivalent von Mises stress is whatever that is in pascals. Um, and we'll print it. Oh my gosh, I forgot that PA is not pascals. And 212, which is in freedom units, 30 ksi. So 30 ksi is what the actual stress is there. And for giggles, actually, we have to rerun these numbers with the new lengths and everything. So we should go figure that out first before we say that we have an answer. So our new length is going to be from essentially here to, it's going to be this length roughly plus this length roughly. So that total length is 85. 35 plus 48. Yeah, so roughly 85. So let's go through and retool all these calcs. So L prototyped, do we actually end up using L prototyped? Yeah. So our B has changed though. I think our B is now, what was it? B is 4. H is the same. Length of the locking tabs, we said that's 85 now. All right, we'll just redeclare here. L is equal to 85. Weirdly, it doesn't look like, no, we have to rework this. So we solved for something before. What do we solve for? Wait, no, we have to rework this because this was yesterday when we were trying to find out. Yeah, this is gonna get more complicated. All right, we're gonna have to rework this. We'll do that tomorrow. After I get the fixed CAD as well. Okay, that's it for today. Thank you for joining. Thank you, Bryce and Jonathan, for helping out. And I'll get that fixed CAD and drop it in here, and we will get back to this tomorrow. See you next time.